Alright, hello physics fans. We are back for a new unit. In this one, we are going to go and sort of try to tie together some stuff. We're going to review back to our dynamics and talk about objects that go back and forth and use that to describe things like waves, and finally to try to put our arms around the phenomena of AC currents. So we've got a lot to do this unit, but things are going to get a little easier for a bit here. So remember at the beginning of this course, I told you about the big picture. And in this big picture view of physics, physicists claim there are only four fundamental forces. There's gravity, described by Einstein's general relativity. There are electromagnetism. That's what we've been spending all of our time on this semester. Then there are the strong and weak nuclear forces, which are all of these. This is our standard model. Now, of course, I have to mention there are dark energy and dark matter, but these are still matters of contention. But all of the rest, all of the electromagnetism, strong and weak nuclear forces, those are all written in terms of field theories. We've already talked about some of these fields, the electric and magnetic fields, which are really part of some underlying single entity. And the best way to describe these that we know about is in terms of oscillating waves. So if we want to master that language of physics, we want to get a little bit better at using the language of waves. So that's a lot of what this unit is going to be about. Now, before we jump all the way down and think about waves, think about field theories, stuff like that, let's go to a much, much simpler example. And this very simple example is called the simple harmonic oscillator. Now, this is quite a boring little system, which just goes back and forth and back and forth. But the description of this is going to be very important for us to understand fully. There is the amplitude, the frequency, and the phase. And all of these things are going to be important in understanding oscillatory motion. Now, let's take a look at this. So if you're following along with this, I really encourage you to write down, what is this expression? You've got a couple different parts. Okay. Now, the first part is this thing in front. This is the amplitude. And for instance, if our displacement, if our oscillation is a ball moving back and forth, then this would be in meters. Of course, you could have an amplitude of a field. I say of course, but who knows whether that's obvious. And so this number is a constant, and the cosine of omega t plus phi, that thing is changing. Now, this amplitude tells you about how big the maximum displacement from equilibrium is. Now, when I say equilibrium, we are presuming in here that there's some force that's pulling our particle back towards the center always. So as we'll see in a couple slides, the simplest version of this is the idea of a little mass on a spring. So imagine you have a spring that's pulling our particle back and forth. If I pull it out here, this is the maximum displacement, and our spring, or whatever force it happens to be, will pull our particle back towards the equilibrium position. Now here's what I want to make sure that everybody notices. Our particle is going back and forth between plus x max and minus x max. And that means that if you just go and look at the distance between the maximum and the minimum, you would actually get a distance of 2xm. Okay, so that distance is that distance from one side to the other is not the amplitude. The amplitude is half of the span of the total distance that our particle traverses. The other thing to recognize in here is the frequency. Now, there's something in here called the angular frequency, but let me just sketch this out a little bit. If you have this expression, xm cosine omega t plus phi. Let's say that for the moment, let's set that phi equal to 0. What this looks like is x versus t, where you start up at some position x max, and then your object goes back to 0, overshoots, goes to negative x max minus xm, and then comes up and returns to the place where it originally was sitting. Now, sometimes when people are seeing this the first time, they will want to call the time it takes to go from one side to the other the period. But the period is the amount of time it takes to get from the very beginning of a cycle back to the identical place in the cycle. Okay, so it's going for if you start out at this x max, for instance, it would be going here all the way over to minus x max and coming back. So the amount of time it takes to do that is the period t. Then if we wanted to talk about the frequency, it would be 1 over the period. Okay, so period is in terms of seconds. If you have frequency, it's going to equal 1 over the period. So that would be 1 over seconds, which is a unit that we call hertz. So for instance, if you had 10 hertz, that means that your object is going back and forth and back and forth and back and forth. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All within the span of 1 second. Okay? Now, what's a little bit confusing is that often in these problems we don't use the frequency, we use the angular frequency. Now, the reason we use the angular frequency is because inside of cosine, the argument allows this function to repeat every 2 pi, right? So if this were 0 and that were 2 pi, we'd be okay. So what the omega does, it allows all this thing that's inside of the cosine function to go through a full cycle of 2 pi every period. Okay, so our omega is 2 pi times the frequency, or 2 pi over the period, and it also just has units of hertz, just like our regular old frequency had units of hertz. Now, perhaps the most confusing part at first is the idea of a phase. Now, this is what I was just talking about with the 2 pi thing. The phase is the part, is the argument of that sinusoidal function. Okay? So, you'll remember that if I have, for instance, x equals cosine of something, if I have the angle at 0, my x would be 0. And this is just going around our unit sphere. Whoops. If I have an angle of 0, my cosine is at the maximum. So here, if we have this at x max cosine theta, then this would be at x max at an angle of 0. It would be at 0 at an angle of pi over 2. It It would be a minus x max at an angle of pi. It would be at 0 at an angle of 3 pi over 2. And then it would be back at x max at an angle of 2 pi. So that phase angle, it's describing the different parts of our oscillation in terms of radians. So it's a little confusing because this is happening in space and time, but we're describing it in terms of an angle. Why are we doing that? It's because we're using these sine and cosine functions as our friends, and so we're kind of halfway using physics, halfway using math, and using all of our tools to describe the system at hand. So let me do a couple dances for you. Let's say that we have two oscillations where the amplitudes are different, but the frequency and the period are the same. Okay, so let me try that. Okay, so this hand, I'm going to have a bigger amplitude, but the same frequency and period. So these are going up and down at the same time. But my right hand, I'm not sure how it's displaying on your screen. This hand is going through more distance. The amplitude is bigger. Of course, you could have the amplitude be the same, so that's me moving my hands at I'm not very good at it. moving my hands at different rates. Like this one could be going up and down faster, this one could be going up and down slower, but they're going up and down the same distance. In that case, you'd have the same amplitude, different frequencies. Then this third one is the idea of being offset by a phase angle. And this one is the best, the best dance. It looks like this. All right, good shimmy. So in this case, both hands are going up and down the same amount. Both hands are going up and down at the same rate, but they're in different parts of the cycle at the same time. So they're offset by a phase. Okay, so here's a homework problem that I gave you on this. It says an object undergoing simple harmonic motion takes 0.25 seconds to travel from one point of zero velocity to the next such point. The difference between those points is 36 centimeters. Calculate the period, frequency, and amplitude of the motion. Well, take a look at this. We know that our cycle looks something like this. You start at your x max. I mean, you could start anywhere, but this is the easiest way to think about it. And you go to some 0, you turn around, you come back, and you go to your x max. Now, what I wanted to point out to you is that here, the slope is 0, so the velocity is 0. Your maxima, your x max and minus x max, are the 2 points where the velocity is 0 because your particle is turning around at those points. So when it says an object undergoing simple harmonic motion takes 0.25 seconds to travel from one point of zero velocity to the next such point, they're talking about this, going from the maximum x max to minus x max. This here is 0.25 seconds. And then it says the distance between those points is 36 centimeters. So from x max to minus x max is 36 centimeters. Now, the reason I'm bringing this up is that I really want to drive home that there's a distinction between these numbers and the period and the frequency and amplitude. So, in the period is the time it takes to go from plus x max to minus x max and back to plus x max. So the period would be double that. The period would be 0.5 seconds. Of course, to find the frequency, you just need to take 1 over the period. So then the frequency here would be 1 over 0.5. It would be 2 hertz. What does that mean? It means that your object goes all the way from x plus down to minus x, back to plus x, down to minus x, back to plus x in 1 second. It does through the whole cycle 2 times in 1 second. This is just 1 second going up, or 1 cycle going up to 0.50 seconds. Then in part C, the amplitude of the motion, well, this 36 centimeters, be careful, that is double the amplitude of the motion. The amplitude of the motion is just half of that. The amplitude from x max would be 36 centimeters divided by 2 would be 18 centimeters. So just be careful about these definitions. Now, I want to point something out to you here. I'll write it just a little bit simpler than this. But if we know what the displacement of x is for a simple harmonic oscillator, so we have x equals xm times cosine of, let's just say, omega t. I'm going to leave off the extra phase, but you could start your time at equals 0 any time. But just this easiest version. Because we know the position versus time, we can always derive the velocity versus time by taking the derivative. The slope of the position versus time graph gives us the velocity versus time. So if I want to take the derivative of this, I've got to use my chain rule. So the derivative of the thing on the inside gives me an extra omega. The derivative of this, derivative of cosine, is minus sine. So my v here would be dx dt, which is equal to minus sine, and then there's an extra omega that comes out when I take the derivative of the thing inside. So it would be minus omega xm sine omega t. Then I can take the derivative again to get my acceleration. And the derivative again would be the derivative of v, or the second derivative of x with respect to t. Derivative of sine is cosine, and then I get an extra factor of omega out front, and so this is minus omega squared xm times cosine omega t. Okay, so the thing to just to make something explicit here. Notice we have this xm cosine omega t here in the acceleration and in the position. So from this we can make a very surprising and important point, which is that the acceleration is equal to minus omega squared times the position. Okay, we'll use that in a second. Now, just to make sure your intuitions are on the right track here, take a look how our motion is actually occurring in this story. You start at some x max, then you get faster and faster and faster as you go through equilibrium, then you start slowing down, slowing down, slowing down. Stop, turn around, start going faster and faster and faster and faster, then start slowing down, stop. That's one cycle. Okay? And you can see that here, right there, you have a velocity of 0 because the slope is flat, or alternatively because it's turning around. And then here, your velocity is maximum. There's the slope where the displacement is 0. Okay, and so the extreme values sort of happen offset by a phase of pi over 4 between your position and velocity graphs. The extremes happen at the same place in the displacement and acceleration graphs. Now, we're going to introduce a simple model. We've established in the last page that the acceleration is directly proportional, just with an extra factor of omega squared. Remember what omega is. Omega is 2 pi times the frequency, or 2 pi over the period of your cycle. And so acceleration at every moment is going to be directly proportional to position. Now this turns out that you can have a very nice model. And the model that we'll have is called Hooke's law. This is Hooke's law. And it says that if you attach a block to a spring and you pull the block away from the spring's equilibrium position, no matter if you squish the spring or if you stretch the spring, it will always try to pull your block back to zero. Okay, so let's see what that means. So just looking at this, K is something that is telling us about the stiffness of the spring constant. It has to have units of newtons per meter. And really, so if your spring constant is 5 newtons per meter, let's say that you could stretch your spring out a whole meter, and it would give you more and more and more force as you pull it further and further and further. If you pull it out 1 meter, it would give you 5 newtons pulling back. Okay, so that's the idea. Now, as it turns out, we can use just this rule and Newton's second law, along with the information that we know that this object is going to be oscillating back and forth, to get our period. So let's see how that works. Okay, so we're starting out with this model that we have a block on a spring, and the force of that spring is always pushing it or pulling it back towards our x equals 0. Now, we presume two other things that we've worked out already. We presume F equals ma. So that's just Newton's second law. And we presume that we have simple harmonic motion such that the acceleration is directly proportional to the displacement. Now let's put this together. Right here, we have a model for how the force is working. It's going to be linearly dependent on how much you displace the block. The more you pull it away from equilibrium, the bigger the force. So here we're going to have minus kx equals ma. But now I'm going to say I assume that that it's following this relationship as oscillating block. It's going to go back and forth and back and forth and back and forth. And so this turns out to be minus kx equals m, too many squiggles on that m times minus omega squared times x. Okay, but now I have x on both sides. X is varying in time, but it's the same on both sides. So I can just say that k equals omega squared times m, or omega equals square root of k over m. Now this is a very nice result because it allows me to immediately make predictions about how the period varies with the stiffness of the spring and the mass that we put on its end. So in this case, omega is just 2 pi over the period equals square root of k over m. So you can find out that the period equals 2 pi square root of m over k. And if you think about it, this actually does make sense, and it is what you find in experiment. You put more mass, it's going to move more lazily. It's going to be harder to get that object to move back and forth. If you take a stiffer spring, on the other hand, it's going to want to pull it harder, and so you get a quicker oscillation. Okay, so those are the two things. Okay, so let's quick do a recap. We've got some position function, and we've already talked about what this form is. X max times cosine of omega t plus some phase offset. It says the position function is this, gives the simple harmonic motion of a body at time equals 2. What are the displacement, velocity, acceleration, and phase of the motion? Okay, now you should be able to immediately be able to just put in t equals 2 in here, and then you're going to have something inside of the cosine function and be able to tell get a number out. The number, of course, is going to be between 6 and minus 6, because that's the range of our possible values for that particular function. So just to put it really explicitly, this and that are the same thing. You just have an explicit example of xm, 6 meters. You have an explicit example of omega, which is 3 pi over seconds, so 3 pi hertz. And then here's your example of your offset angle. Okay? And because you know how to do all the rest of this, for instance, we found that v is going to be dx dt. We already looked at this, with a very general and abstract version, but you could also do it with one that just has all the numbers in it. This would give you minus 6.0 meters times 3 pi radians per second times sine of 3 pi per second times time plus pi over 3. Of course, you want to be careful to make sure that your calculator is in radian mode when you stick in these numbers, but there's nothing really that difficult about sticking 2 in there and then getting a number out for the velocity. And of course, for your acceleration, you're going to have to take the derivative again. Okay, so you'd have to take the derivative of that to get your acceleration. The part that's a little tricky is to find, it asks what the phase of the motion is. The phase is just this thing in here. Okay, so it will have units of radians. If you put in time equals 2, you can have 3 pi times 2 plus pi over 3, and you will get an answer that is in radians, and that would be the phase. Then, of course, from that angular frequency, you should be able to find the frequency and period of motion, because frequency is just 2 pi, other way around. Omega is 2 pi times frequency. So from omega, it's easy to find frequency. And once you have frequency, the frequency is just 1 over the period. So you can also find the period. Now I'd like to do just one more example of a simple harmonic oscillator, and that is the pendulum. And the pendulum is a little bit more involved, simply because it harkens back to our angular motion from last semester. So The physics is not that hard. It's just that we have to remember our stuff about torque, our stuff about how torques cause angular accelerations, and how there's this thing about the moment of inertia. So let's just quick go through the problem. What happened here? Okay, so let's just work out the problem. Here, at some angle offset, the force that's acting on my bob, my pendulum, is going to be minus m times g. Now the torque is r cross f. And remember, r is relative to the axis of rotation. So there's your axis of rotation, and this ball is swinging like this. And so if this length is L, that would be L, and the force is going to be minus mg, and then so that's our force, but this is a cross product, so we do have to care about the fact that there's a sine of theta in there. Sine of theta. Okay, and that theta is the angle between the vector pointing from the point from the axis of rotation to the particle and the force. Now, our second one is that torques cause angular acceleration. Remember, angular acceleration is just the second derivative of angular position, just like acceleration is the second derivative of regular old displacement. Okay, so there's my torque. And then the last piece that I need here is what my moment of inertia is. So the moment of inertia is the mass times the distance squared to the center, to the axis of rotation. So in this case, it would be the mass of the little bob at the end times L squared. Now let's put this in. Let's put this in on either side. So for my I times alpha, I would have m L squared alpha equals, and then for my, so that's this side, and then for my torque, I'm going to have all of that stuff right here. So I'd have minus m L g sine theta. Now, to go further in this analysis, it's going to be useful to remember that if I keep my, if I'm dealing in radians here, it turns out that sine of theta and just theta look very similar. So this is y equals sine of theta. This is y equals theta. If you go close to the origin, they are right on top of each other. So if we work just with little oscillations, just going around the bottom here, I can replace that sine of theta with a regular old theta. And so I'm going to divide both sides by ml squared. Okay, so I get alpha, that's my angular acceleration, equals minus, the m's surprisingly drop out. I have L over L squared, so I have L in the denominator. So here I have G over L. And then instead of having sine of theta, I'm going to write theta. Now, what sort of motion is this? Well, as it turns out, this is essentially the same as when we wrote A equals minus omega squared times x. Angular acceleration equals minus some number times angular position. acceleration equals minus some number times displacement. Okay, so what we can do now is identify these types of quantities with one another. So we say that omega squared equals g over L, or omega in this case is going to be the square root of g over L. So, kind of a surprise, the period here, okay, omega equals 2 pi over the period equals square root of g over L. So, if we want to use that, we have essentially that our period is just 2 pi times the square root of L over G. So, what does this mean? G is just that 9.8 meters per second squared. The period of a pendulum just depends on its length, nothing else. That assumes, of course, that the mass of the pendulum is all right at the end. Okay, so we put in all of our approximations, and then we said when a mass is concentrated at the end of a pendulum, its period only depends on its length. So just to make sure that we are thinking about our two examples, we've got our pendulum where the omega is equal to square root of g over L. And we have our mass and spring where the omega is equal to square root of k over m. Okay, so it says the mass of a pendulum bob is m. Similarly, the mass of a block attached to a spring is also m. The constant of the spring is selected so that the pendulum and the block oscillate at the same frequency. What effect would there be on these two systems if the mass of the block and the bob is increased to 2m? Well, I hope that you can see that in the case of the spring, you increase the mass, you decrease the frequency. In the case of the pendulum, you increase the mass and nothing happens. So the frequency on the block decreases. It essentially accelerates less quickly, and the frequency of the pendulum is unchanged. All right, so we've gone through some good start on our simple harmonic motion. We've talked about the amplitude of motion. We've talked about the frequency of motion. We've talked about the phase of motion. And then we finally talked about two great examples, the pendulum and the mass on a spring. Okay, so you might not think that this is enough to get you going, but I encourage you already after watching this video, you're going to be able to do a lot of your homework for this week. So go forth and succeed.